Hi, so sorry about this video coming out later than I had originally said in class, but I got caught up today and I didn't get it done before I left work. All right, so anyway, I wanted to go through one more example, actually a couple more examples from 14.1. I was looking at the homework assigned in my math lab, and this first problem written here on this sheet is finding the points of intersection between a given plane and a vector function, all right? And I think the last couple questions in your homework asked you to do that, and then we did not do an example like that today, so we're going to start with this one. All right, so find the points if they exist at which the plane and the curve intersect. So our plane given is y minus x equals 0, and then our vector function 5 cosine t, 5 sine t, t. The key here on this one, and I'm sure on any that you will encounter, is to pay attention to your window. All right, you're looking for intersection points within t values from 0 to 4 pi. All right. Okay, so what has to happen here is if y minus x equals 0, that's the same thing as saying y has to equal x. All right, so if y equals x, if I look at my vector function, I'm going to set the y and the x functions equal to each other. So 5 cosine t equals 5 sine t. And then I'm going to solve that equation for t. All right, so I can divide both sides by 5. That gives me cosine t equals sine t. So I have to find all of the t values between 0 and 4 pi where sine and cosine are equal to each other. All right, so over here I drew this little unit circle. All right, here's the line y equals x, this diagonal line straight through the middle. So where that line intersects my unit circle is where this is going to happen. Right, it's going to happen over here in quadrant 1 at a 45-degree angle. Right, sine and cosine would be the same. And then again down here in quadrant 3, because down here is, so up here is where you have them both have a positive value, and down here is where they're both negative. Okay, for that those two spots. All right, so if I'm at 0 right here on the x-axis, if I rotate up here to pi over 4, sine and cosine are the same. So pi over 4 is my first value of t. And then I rotate all the way back down to here. That lands me at 5 pi over 4, where they're equal again. So that's my second solution. And then I come back to here. So when I get back to the x-axis, I'm at 2 pi. So if my window was 0 to 2 pi, those would be my only two solutions. But I have to go around again because I have to be 0 to 4 pi. So if I'm at 2 pi here and I rotate up another pi over 4, this would be 8 pi over 4 plus pi over 4. That would be 9 pi over 4. So that's my third solution. And then all the way around to here, this would be at 13 pi over 4. And then finally, coming back around that second time, I would be at 4 pi. Okay, so because you have the window 0 to 4 pi, you have to go around that circle twice. All right, so I have 4 values of t that solve this equation. All right, so I'm looking for intersection points. So the values of t, or the points that they're looking for, are the ones that would be generated by plugging those values of t into my function. So at pi over 4, if I plug in t equals pi over 4, I get 5 cosine pi over 4 plus 5 sine pi over 4, and then pi over 4. So that value, cosine at pi over 4 is root 2 over 2, as is the sine. So I get 5 root 2 over 2, 5 root 2 over 2, pi over 4. When I plug in 5 pi over 4, the only difference is both sine and cosine are negative root 2 over 2. So these two coordinates change sign. And then my t value also changes because I plugged in a different t, so 5 pi over 4. Then when I get back to 9 pi over 4, the sine and cosine values are the same as they were at pi over 4, so those x's and y's still become 5 root 2 over 2. But my t value this time is 9 pi over 4, so that's my z component, right, from up here. And then finally my last one, 13 pi over 4, gives me, that was where I was back here in quadrant 3, so I get the negative 5 root 2 over 2 for both of x's and y's, and then my t value again for z as 13 pi over 4. All right, so I don't know, everybody's going to have probably a slightly different version of this, okay, but if your window 0 to 2 pi, you just have these two solutions. 0 to 4 pi, I have these 4. If it was 0 to 5 pi or 6 pi, you may have more, okay, so pay attention to that. All right, the other thing out of that section we had talked about that I was going to go over in this video are identifying what the graphs of some of these three-dimensional functions are going to look like. All right, so we're going to look at some matching problems in the book here in a second, but let's just take this one for example. All right, if I was trying to describe or identify what the graph of this would look like, we talked about this a little bit in class today. Notice in the sine, or in the x and y spot right here, we've got a cosine of t and a sine of t, and they have like coefficients. Okay, but then our z value here is not constant like it was on the example that we had done today. This is a linear expression. So what that means is in the xy plane, because I have a sine t and a cosine t function with like coefficients, that forms this circle, x squared plus y squared, in the xy plane. And then, so if you were to not have z at all, that would be a cylinder running in the z direction. So then when you put in your t value here at z, your curve is going to land along the path of that cylinder running upward, or up and down, depending on if you use positive or negative values here. So I know it's kind of hard to visualize when we're not drawing the picture. So let's look over here at the book, and I want to show you a couple things about what those look like. Before we do these matching problems, let's go back and look at this example. All right, so here's a similar problem. All right, and these are nice if you look through the actual examples in the text with the cylinder actually shown. It's a little bit easier to see it. So this is the graph, the black curve, for the function r of t equals cosine pi t sine pi t e to the negative t. So notice again, in the x and y positions of the vector function, you have a cosine function and a sine function. They have the same angle, and their coefficients are the same. So notice this x squared plus y squared equals 1, this circle of radius 1 here that forms this cylinder that runs up and down. The path of that curve lands along the outside of that cylinder. And it follows the shape generated by plugging t into this z component. So your z components, your x's and y's always stay within your cylinder, but your z component changes based on what the z coordinate is when you plug in different t's. All right, so you see it spiraling upward in this fashion where it's close together at the bottom, and the further it goes up, the further apart the curve spreads from each other, right? Because of this function that sits in the z position. I'm going to scroll backwards again here and just kind of go through another one of those before we look at some problems here. Here's another one. Notice this one has a cosine of t in x and a sine of t in y, and it has, in the z spot, it has another sine function, but this sine function has a different angle. So again, in the x and y positions, that's going to form, if I just look at x and y, that's going to form a circle in the xy plane, shown right here in blue. And then the z component of your ordered triples, generated by that vector, follow along that cylinder path, right? So this vertical cylinder from that xy plane, but it rotates just up and down like this function would, the sine function, right? So that's why it looks like that shape. All right, so kind of keeping that in mind, let's go and look at some of these problems in the book where they're asking you to match. All right, so we've got these 6 vector functions given, a, b, c, d, e, and f, and then the capital letter A, B, these 2 graphs, along with the 2 up here, or the 4 up here at the top. So we're looking to match the function with its graph. Okay, so these are all a little bit of a different shape. So let's go one by one and talk about what you have to look for here. All right, so for A, you've got r of t equals t, negative t, t. All of these functions in each spot, in the x, y, and z spot, they're all linear, right? So this has to be the graph of a line. Okay, our parametric functions that we did for equations of lines earlier in chapter 13 are vector functions that represent a line, right? So all of these are line expressions or linear expressions. So if there's a graph that is a line, it has to be that one. This one's not a line, neither is this one, so that's not it. These 3 are not lines, so the only possible option is this one right here, E. If you had more than one line and you had to pick which one it would be, All right, once you knew it had to be aligned, you would just basically go through and choose different values of t, find a few points, and then pick the line where those points were on it. So here, if I pick, say, 1, I get 1, -1, 1. And if I pick 2 for t, I get 2, -2, 2. Right, so then if I had more than one line that I was having to decide between, you would have to pick the one, right, that had those points. All right, B, we've got t squared, t, and t. All right, so here, notice in the x spot, we have a t squared term, right? So that would be the shape of a parabola toward the direction of the x-axis. And when I square t, because it's just t squared here, that means all my x components, or all my x points on my curve, will have to be positive, because no matter what I plug in for t, when I square it, I can't get a negative result. So I'm looking for some graph that resembles a parabola toward the positive x direction. Okay, these two do not look like parabola shapes. But up here, this one, D, right, looks like what I was describing, right? It comes out toward the positive x-axis in the form of a parabola shape. And it doesn't go back here and hit any negative x values at all. So that one has to be D. All right. C, notice C, D, E, and F all involve trig. Okay, so they're all going to be some form of a spiral or a circular pattern. All right, so for C, you've got 4 cosine t, 4 sine t, and 2. So notice in the x and y positions, we have sine and cosine functions that have the same angle and like coefficients. So within the xy plane, it has to land on a cylinder that runs in the up-down direction. All right, and then the z component here is constant. It is 2. So this is like the one we did in class today. The one we did in class today had a constant x value, right? So we just saw that two-dimensional shape in the yz plane. This is going to have the circular shape of this circle sitting up at a z value that it stays constant at 2. All right, so this graph does not have a constant z, nor does this one, so it cannot be the right one. This one doesn't. This one we've already used the other two, so this is clearly your choice here. Right, notice your axes on these are not scaled, right? So you just have to basically look for shape. But this circular shape is the circle, right, formed by the sine and cosine function within the xy spot, because it sits parallel to your xy plane, right? And that's a circle that sits up at the constant value of z equals 2. So that one is F. All right, let's look here at E real quick. This is similar to the one we looked at in the example in the book. It's got a sine and a cosine in x and y, and it's got another sine pattern with a different angle in z. Right? So that's similar to that roller coaster curve that we looked at as an example that looks like A. It sits along the cylinder. They don't show the cylinder here, but if they drew in the cylinder that runs up and down in the xy or in the z direction, right, this whole graph is on that surface, and it follows the shape of the sine curve, right, this up-down shape like this, in the vertical direction represented by the z component. All right, and then these other two, notice, are similar. This one is a spiral curve coming out toward the y direction, the one I haven't used, and this one is a spiral coming out toward x. Okay, so they should have similar vector functions. So let's compare D and F. All right, notice these are almost the same, it's just they've rearranged the functions. Here you've got sine and cosine sitting in the y and z spot, with the linear term sitting over here in the x position. So this should form a spiral that would project back onto the yz plane into a circle, but it should flow out toward the direction of the x-axis, because that's where the linear piece is. Right, this one comes out toward y, so that doesn't look like it's going to be the right one. However, this one shows that spiral moving out toward x. So that's going to be C. And then by process of elimination, it leaves F to go with B. But why would that make sense? Sine and cosine are in x and z. And the spiral, right, should flow out toward the direction of y, because that's where your non-trig function is, right? And it's not constant. So that's why it's not just a circle sitting somewhere, but it's a spiral like this that moves out If you were to project this back onto the the xz plane, it would form the unit circle formed by the sine t and cosine t. Okay, so that's kind of what you're looking for in terms of graphing three-dimensional vector functions as opposed to two-dimensional. Okay. Okay, so that's the end of chapter 14. I just wanted you to at least have some explanation on how to finish those homework problems. All right, so we're going to go back here to this sheet of notes here and talk a little bit about 14.2. All right, so in 14.2, I'm going to skip around a little bit because some of the things in there I think are going to be harder to learn just by watching a video versus going through those examples together in class. So all I'm going to do in this video for the 14.2 is talk about how to do derivatives of vector functions and how to do antiderivatives. Okay, we'll get into all of the other applications or other types of problems that are in that section when we get back to class on Monday. Okay, so if you want to start any of this homework before then, you might have to skip around a little bit. All right, so the derivative and the tangent vector. So if you have a vector function, r of t equals f of t, g of t, h of t, then r prime, meaning the derivative of that vector, is simply f prime, g prime, and h prime. You just take the derivatives of each component separately, just like we did the limit problems. All right, provided that derivative is not the zero vector, it forms what we call a tangent vector corresponding to the point at r equals t. So for example, if you have this vector function that flows in the positive orientation where the arrows are indicated here, and say we have a point right here, r would be the vector starting at the origin, ending at this point, and then r prime would be tangent to that curve, pointing toward the direction of the arrows. So instead of a tangent line, like you've seen in Calc 1, right, that would go both ways, the tangent vector, right, points toward positive orientation, but is still tangent to your curve. If the arrows on this curve pointed the other direction, this vector here would be tangent, but it would point backwards this way. Okay? All right, so we're just going to go through some basic examples of finding what the derivative functions are. So find r prime. R of t equals tangent of ti plus secant of tj plus cosine squared of tk. So r prime is going to be another vector consisting of the derivatives of each of those functions. So the derivative of tangent is secant squared. The derivative of secant t is secant t tangent t. And to handle this one, you'll use the chain rule. Cosine squared of t is cosine of t squared. So that derivative, the 2 would come down to the front. So you get 2 times the cosine of t to the first, and then times the derivative of cosine. Let's look here first. So 2 cosine of t to the first, and then the derivative of the inside is negative sine, the derivative of cosine. So if you clean that up, you get negative 2 cosine t sine t, and that's fine. That does happen to be the double angle identity for sine of 2t. The 2 cosine t sine t is sine of 2t, so changing it to that would be fine as well. These others we would just leave as they are. So notice your answer is a vector, right? It just has the derivatives in each component. All right, part B, find the tangent vector for t equals 0 for this function. So same thing, tangent vector means derivative. You're just going to plug in a value of t when you're done. So this gives us r of t is e to the t, e to the 3t, e to the 5t. So r prime, derivative of e to the t is e to the t, derivative of e to the 3t, e to the 3t times 3, and for e to the 5t, e to the 5t times 5. So if it just said find the tangent vector, that would be it. But it wants you to find it for t equals 0, so now we're just going to plug in 0 for t. So e to the 0, 3e to the 0, 5e to the 0 would be 1, 3, 5. Still a vector, right, but it's just been evaluated. All right, higher order derivatives of vector functions work just like you would think. Second derivative is the derivative of the first, and the third derivative is the derivative of the second. Okay, we'll have a need for those later. They come up in formulas we're going to see later in this chapter. But for now, just finding those derivatives. So here's the function they give us. So r prime would be 3 times 12, 36, t to the 11th minus 2t, 8t to the 7th plus 3t squared, negative 4, t to the negative 5th, just the power rule. So the second derivative, 11 times 36, 396, t to the 10th, minus 2, Here you're going to get 56 t to the 6th plus 6t, and then here you're going to get positive 20 t to the negative 6th. And then for the third derivative, one more time, bring down the 10 and multiply, 3,960 t to the 9th, 56 times 6, 336 t to the 5th plus 6, and then negative 120 t to the negative 7th. Okay, just normal derivatives rules from Calc 1. All right, integrals of vector functions work exactly the same. All right, so if you needed to find the indefinite integral of a vector function r of t, you get its antiderivative vector plus a constant. Notice these are still vectors, okay? C is a constant vector, and the capital R is the function consisting of the antiderivatives, right, from the original vector that you were given. Or in other words, antiderivative of this is the new vector, capital F, capital G, capital H, where these capital letters are the antiderivatives of the lowercase letters, plus a constant at the end. Make sure the vector at the end is a constant. All right, so how would that work on an example? So let's try this one. 5t to the negative 4th minus t squared, t to the 6th minus 4t cubed, and then 2 over t. So we want to find the antiderivative of that vector. So we're going to get another vector. We're just going to take the antiderivative of each part, and notice here it says plus c. So if this vector c, say, had component c1, c2, c3, we would be adding those. So we would just use our vector addition rule for addition. So I'm just going to do that here as I go. All right, so antiderivative, you add 1 to this power, that gives you a negative 3, and then you divide by that new power. So you get 5 over negative 3, t to the negative 3rd, minus, this would be t to the 3rd over 3, plus c1, right? You'd have a constant in each of those positions. Here you get t to the 7th over 7, minus, here when you add 1, you get a 4, divide by 4, right? Cancels the coefficient, so that's just t to the 4th plus c2. And then the 2 constant just stays there. 1 over t antiderivative is natural log of the absolute value of t plus c3. If this comes up in my math lab, you may need those absolute value bars around the t, so just don't forget about that. All right, and then otherwise that is a vector, right? And that's the answer. All right, if it was a definite integral, the only difference is once you do each antiderivative, you evaluate it between your limits. So this time you get numbers, right, for each of those components. So the antiderivative from 1 to 4 of this vector function, notice it's a vector with the ijk. So we're going to do the antiderivative of the f function from 1 to 4, the antiderivative of the y from 1 to 4, and the antiderivative of z from 1 to 4. All right, so here you're going to get t to the 3rd divided by 3 would make this 2t cubed between 1 and 4. So 2t, or 4 to the 3rd minus 2, 1 to the 3rd simplifies to 126. Same thing for the second function here. T to the 4th divided by 4 makes the coefficient a 2. Evaluate from 1 to 4. So 2, 4 to the 4th minus 2 times 1 to the 4th. You clean that up, you get 510. And then for our last component, t to the 3rd divided by 3 makes the coefficient here a 3, right? You're dividing the 9 by 3, and then from 1 to 4. Again, plug in your top and bottom and subtract. This time you get 189. All right, so just make sure you're writing the answer in vector form. So 126i plus 510j plus 189k, or the other format, the vector with 126, 510, and 189. Okay, so just basic antiderivatives for indefinite integrals and basic derivatives of vector functions. So there's a few other things in that section that we will have to cover in class on Monday, but that at least gets you through the basics. All right, I did move the homework assignment for 14.1 back a week. All right, it was supposed to be due this Sunday, but since I had to cover some of that information in this video, I went ahead and moved it back just in case you have questions. Okay, so you can certainly do it, but it's not due this Sunday. All right, okay, so that's it. No class tomorrow on Friday, and I will see you back in class on Monday. Have a good weekend.